one thing that distinguishes us from most other animals is our ability to engage in what we'll call mental time travel. Mental time travel. You think of something as fundamental as the invention of agriculture. Plant a seed, reap the benefits later. That was a very hard step for us to connect the temporal dots over weeks, months, and years. Can you imagine what it was like for the first human to make this cognitive leap and say, oh, I'm going to die? Right? Because it's this ability to engage in mental time travel that we became aware of death.
This is StarTalk Special Edition. Today, we're talking about the time machine of the mind. Ooh, what does that mean? Well, let's go to my co-host here, Gary Riley. How you doing, man?
I'm good, Neil. We're all back in our man caves remotely, so it's a bit strange from being in your office again.
I miss my office.
Yeah.
And Chuck, actor, comedian.
Yes, I am. I'm actually not here, guys. I'm in the future.
You're in the future in the time machine of the mind.
I'm in the time machine of my mind, talking to you from there.
Well, Gary, you and your producers cooked up this episode, and it needs good ingredients to do the right thing for it. So tell me your thinking.
All right, let's put it this way, shall we? Is time an illusion? All right, hold on to that thought for a moment. And from moment to moment, we transport ourselves backwards and forwards in time in our own brains, remembering the past, projecting to the future. But how does that all work? In today's episode, we are going to wrap our heads around time. Well, we're going to try to wrap our heads around time, and time as we know it in physics and how we experience it in our own brains. How do we tell time? Why do we tell time? And finally, is time travel possible, but only in our minds? Okay, that's the tease. Let's get to our guest.
Well, it's a very rich topic that's even been addressed in many a film. Mm-hmm. And so I'm curious to see how much of that is plausible or just fantasy. So we introduce, we're growing our list, our stable of neuroscientists, because that's the coolest frontier science out there right now.
Oh, yeah.
We got Dean Buonomano, professor of neurobiology and psychology at UCLA, UCLA, as the non-informed folks might call it. You're author of Your Brain is a Time Machine, the Neuroscience and Physics of Time. That's what really got us interested in your work. So we are delighted to know this. Oh, by the way, Buonomano, we were speaking offline. I would have guessed that meant good hands in Italian, that you come from a long line of surgeons and other people who do good things for people. But you disavowed me of this.
Yes, we're more on the sketchy side of that. So I think we're mostly pickpockets.
Pickpockets.
Hey, listen, you got to have some really good hands to be a good pickpocket.
Yeah, I mean, I think it's underappreciated. Exactly right.
Yeah. Like, you have never heard a pickpocket say, "Oh, I'm off thumbs today." Like,
That's true.
It doesn't happen.
And maybe Neil's correct in that there's a connection there that the original pickpockets became surgeons. Because,
makes sense.
So tell us how, I could talk the physics of time all day, but that's not why we're here. We want to know the neuroscience of time. So tell me how the brain tells time.
I wish I knew, Neil. No.
Then why do we have you on
your guess is as good as mine.
Give me your graduate student. Give me somebody who knows something.
So I think to answer that question, it's helpful to think about man-made clocks. And I think man-made clocks are a bit underappreciated, right? And that through history of civilization, we've been on a quest to make ever better clocks, right? From sundials to water clocks and eventually pendulum clocks and quartz watches to atomic clocks. And today we measure time better than we measure anything else. So even a meter is defined by how far light travels in some specific fraction of a second. So we wouldn't have a good definition of a meter without really good clocks. Now, all these clocks, they can be sophisticated mechanisms, but they rely on a very trivial principle, which is sort of just counting the oscillations of a time base. That time base could be just the swing of a pendulum, the physical vibration of quartz crystals.
It's something that repeats. Just anything.
It repeats. That's all you need for a time base. Something that repeats in a highly regular manner.
And we had that in astrophysics because Earth rotates, that repeats. Earth goes around the sun, that repeats. The moon goes around the Earth, that repeats. So that we had some built-in repeating things in the universe to jumpstart us.
So, and that was the original clock. The sun.
I was going to say that had to be the original clock. It's like, sun goes up, sun goes down. And then, of course, without an understanding of that, you're like, oh, the sun is losing to night. Night is going to take away the sun.
Yeah.
Let's sacrifice some kids.
God is tucking in the sun for tonight. So.
Right.
But
gotta make sure the sun comes back.
Yeah.
Sacrifice something. Yeah.
But the principle is very simple, right? Just counting the ticks of some sort of time base. The brain does not work like that. So the brain, unlike these clocks on our wrists, which are amazing devices, right? Because the same device can tell nanoseconds, milliseconds, seconds, minutes, hours, days, and beyond. When I'm snapping my fingers to the right, it takes a certain amount of time to arrive in the right ear and the left ear. It takes approximately a few hundred microseconds more to arrive at the left ear from the right ear. And that's how we use information, auditory information, to determine the location of objects in three-dimensional space. But you can also tell time, of course, on the circadian time of many of hours and a day. But they're totally different clocks. So the clocks in our brain that are responsible for seconds, they don't have an hour hand. And the circadian clock doesn't have a second hand. So this is fundamentally different from how our man-made clocks are working. And they also, for the most part, don't rely on an oscillator. They rely on dynamics. So the better analogy would be an hourglass. So they're just falling. So you have the laws of physics governing the dynamics of a system. And the brain is the most complex dynamical system we know of. And it has these patterns of activity. And these patterns of activity are what we use to tell time on the time scale of seconds and sort of what you're doing right now, which during this conversation.
So the circadian clock is based on the rotation of the Earth, correct?
Well, its goal is to match up with the rotation of the Earth, but it's of course based on a biomolecular mechanism. So it's actually has this very sophisticated name called the transcription translation autoregulatory feedback loop, which all that means is that DNA makes RNA, which makes proteins, and those proteins inhibit the further synthesis of the DNA. So you have this oscillation that approximately matches the 24-hour rotation of the Earth.
And so why is it that sight and circadian rhythm seem to be linked in some way? Because what you just said in that oscillation, it would seem like they would not. But we know that blind people sometimes have a drift in their circadian rhythm or their circadian internal clock.
Well, doesn't that also happen when you isolate people away from the day and night cycle, and that their natural cycle that is not exactly 24 hours? So that would drift. That's basically the same thing as being blinded to a daytime rhythms.
Right. Both of those things are true. And of course, so the major, the sort of the master circadian clock, and I want to make that clear, it's just the master circadian clock, not for music or anything else, is in the part of the brain called the suprachiasmatic nucleus.
Wow.
The chiasm here refers to the optical nerves that are crossing over, and it's right above. So why is it associated with vision, Chuck? Well, it's because this goes to Gary's question, that's how it's entrained. So if you drift, if you're in a sensory isolation experiment, which people used to do these, people would spend 2 months in a cave away from light, then you drift little by little. But we use the circadian part, the visual part, to entrain our circadian clock. Here, and to understand why that's important, one of my favorite experiments, a very simple experiment in biology, is maybe you know some people who really almost always go to bed early and they have to get up early in the morning. There's something that's sort of this advanced sleep phase syndrome. And this is a mutation in the proteins that underlie the circadian clock. And the circadian clock can have a different period. So maybe it's 24 hours. And one of my favorite experiments, this is not in humans or anything, this is in cyanobacteria. So these are just single cell organisms that, like us, have a circadian clock. And you might be wondering, why do they need to tell the time? They don't have a schedule to fix, to meet, right? And the reason is because they need to know when the sun is going to rise. because they need to engage the protein machinery to start doing photosynthesis. So what they did in this experiment is they got some mutations that had an abnormal period of 22 hours, and another set of cyanobacteria that had a period of 26 hours. So they're both off, but they put them in the incubator in the same petri dish. So they're competing with each other for nutrients. One incubator had a period of 22 hours. So it was lights on for 11, lights off for 11. And then the other one, it was 13 on, 13 off. And sure enough, in the 22-hour period incubator, only the cyanobacteria that had the 22-hour clock survived. And because they won out the competition. But when they were in the 26-hour incubator, it was the other mutation that survived. So we need to tell time in order to engage the body, the proteins, and the brain to anticipate changes in our environment. And that's extraordinarily valuable.
Wow. Look at that. So for us, on a biological level, time happens all the way down to a cellular molecular level?
Absolutely on the scale of circadian clocks, Chuck.
Okay,
so
right.
Not for seconds. You're
right.
On the circadian level. You are not going to have cells playing music in adagio or grave, right? But for the circadian clock, absolutely.
And I got to remind people, because cyanobacteria are very important in the history of life on Earth, because they were the first species to put oxygen into the air. And that enabled animal life to rise up and become everything that it is now.
What was it before that, Neil? What didn't they kill by putting all the oxygen in the air?
Yeah. So there are plenty of land life forms where oxygen would be hostile to their survival.
Right.
They're all gone. Whatever they were, they're gone. So we owe a lot to cyanobacteria. So I'm delighted that there's this extra research going on.
For our saviors.
They're our savior. That's correct. That's correct.
Dean,
you're our creator.
There must be a reason why humankind has evolved to need to tell time.
Yeah. And why we, throughout history, paid so much attention to telling time. Like, why did we spend so much time early on trying to develop clocks, right? And in many ways, as Neil will certainly know, there's a very tight coupling between the early days of physics and astrophysics and astronomy and clocks, right?
Yeah,
So,
in fact, Galileo, my favorite Galileo stories, I mean, he basically first demonstrated that why a pendulum would make a good timekeeping device, because he was in church one day, and it must have been the summertime because windows were open and there was a breeze, and he was bored. It's a Catholic ceremony. So
that makes sense.
people know what that And so the breeze was coming in and the chandelier was swinging, and not paying attention to the utterances of the priest. He's watching it, and he noted that when it was swinging wide or when it was swinging narrow, it took the same amount of time to complete a swing. And how did he know this? He checked it against his pulse. And so, assuming he wasn't getting excited during this moment, that's as good a timekeeping thing as you could have, on your own out there. And so he concluded that a pendulum, within limits, if it swings slowly or swings a little bit or a lot, it's the same period. And if that's the case, you can put pendula in clocks, and that'll be a sort of a self-regulating mechanism. That's my favorite, just a curious scientist who's bored and just makes a discovery.
That had to be the worst homily ever. My God.
no, it was well timed. It was but to go back to Gary's question, imagine what life would be if we couldn't anticipate what was about to happen. How would you be able to interact with each other, and how would you be able to catch a prey, catch a predator, avoid a prey, or avoid a predator, right? But just to show you the importance of time in culture and society, we talk about the Industrial Revolution, and the steam engine was sort of the, if you will, the engine of that advance. But in many ways, other people have argued that the real engine of the Industrial Revolution were cheap clocks, because that's when we started having factories. If you have a factory, you need to synchronize human behavior. You need to get everybody at the factory at the same time.
I thought that's what coffee did for everyone.
That helps. That certainly helps. But it gets people hyped up, but not necessarily in synchrony, Neil. Mm-hmm. So without that ability to synchronize things, then we wouldn't really have the Industrial Revolution, because you had to synchronize those factors because we needed to work together. And we've always needed to work together. So cooperation in many ways requires timing. As you know, you might know from, here's another football or soccer analogy there, people synchronize their movements together. So when people are clapping, whether it's at a sporting event or in a concert, we naturally synchronize our movements. So we're incredibly attuned to each other's actions, and we use our internal clocks in order to achieve that. And then, of course, with Einstein, then, of course, a lot of that initial goals in terms of synchronizing clocks was due to train schedules, right? They needed to synchronize train schedules in different parts of Europe. And that was another fundamental breakthrough for the economy that couldn't happen without reliable clocks.
Yeah, especially since train schedules are not every city at the top of the hour. It's like it took 33 minutes to get between these 2 points. So you want to be on the track 33 minutes after the hour. And I want to just close the point on the pendulum clock. So Galileo noticed this about the pendulum, but he's not credited with inventing the pendulum clock. There would be Christian Huygens.
Huygens.
And in fact, there's a probe named after him that landed on Saturn's moon, Titan. It's called the Huygens probe, made by the Europeans. That's just an aside. Anyhow, he published a book called Horologium Oscillatorium. And in there is a full discussion of timekeeping via pendulums. And so, yeah, things we just take for granted or even discard were major advances in our attempt to keep time. And that's getting back to, that's answering your question, Chuck. Humans figured out that this is a good thing to know how to do. And then you could do other things as a group rather than be the lone wolf out there. Yeah.
So basically HR is responsible. It's HR, because we need to be able to write you up for being late. That's what this is about.
Punching the clock?
Right.
That's it right there. It's all about the punch clock.
How, Dean, were we sensing, feeling time without the addition of clocks? Because we're not perceiving it second by second, or are we? Does it flow? Is it something? Does it not?
And can I add to that? Were we, and we're talking about, of course, earlier man, because we know how we sense time now. We don't really need to sense it. We just look at our wrist or our phones or whatever. We don't give a damn. But back then, what Gary just said, were we really sensing it, or were we looking for environmental tells to alert us?
Oh, interesting.
Yeah.
Was it from the outside or from within?
Was it from within, or was it really our environment that was kind of saying? And then also, just one last point to put on top of Gary's point, did the repetition of that environmental tell then become inculcated or incorporated within our sensory perception?
I mean, evolutionarily.
Evolutionarily, yeah. And that might be a lot. Maybe I'm way off base here, but you know.
So let me just be clear here. All mammals, so with a developed vertebrate and nervous system, tell time. And it's absolutely important for, on the scale that we're talking about, for interaction with each other. And you think about something like language, right? So language is very temporal. And here's one of my favorite examples. I want to say 2 sentences. The order of the words is the same, but the meaning is different. So they gave her cat food, or they gave her. Okay, you guys anticipate. You guys are way ahead of the game. You guys are way ahead of the game.
That's because we're smart. We figured out what you did there.
They gave her cat food, or they gave her cat food. Right. So you're naturally paying attention to the timing and the intervals, and that's altering your communication. And it's totally unconscious, right? You're not thinking, oh, the pause was different. So that timing is always going on. Now, Gary's original question was perception of time. That often means the conscious perception of the flow of time, which is a very deep philosophical question that implies consciousness. So one of the most salient percepts that we have is that time is always flowing. And this reaches at the core of something that has tension with physics and neuroscience that I've written about, and I'm sure you have talked about. So
the flow of time implies some self-awareness of an arrow of time, correct?
Yes, generally the case, because it's generally flowing forwards. Yeah, I would say that's correct.
From the past to the future. Yeah. But in there, if I see someone of my family and I see them get old and die, does my self-awareness that maybe I'll get old and die too, is that part of my sense of the flow of time?
Yeah, that's a great question. That I want to come back to that specific point about death. But first, in terms of the perception of time, so many physicists would argue that the perception of time, the flow of time, that the past is no longer real, the present is real, and the future is not yet real, is an illusion or a mental construct or something imposed by the brain. And this is the debate between what we call eternalism, or the block universe, and presentism. So under eternalism, the past, present, future are equally real. And under presentism, only the present is real. And that's how we perceive. And this is this fundamental debate about what's the nature of time. And there's this ongoing debate where the physicists say, hey, you neuroscientists figure this out because obviously time is not flowing. Why does it feel like it's flowing? And then the neuroscientists say, well, you physicists figure this out because, time is flowing. But there's two points in physics. And the physics, and it will be interesting to hear all of your opinions, but the physics is really most of an interpretation in which, because of relativity, because the physics doesn't have a specific point, you are here, it doesn't say there's anything special over here. The equations of physics are time symmetric or time reversible. So that leads to one interpretation that the past, present, and future are equally real, much like space. You can be anywhere in space, you can be any moment in time. But I've argued, and that I think the brain is telling us something true about the physical universe, that it is because we evolved to survive in a universe governed by the laws of physics, in a mesoscopic part of that universe, not at the micro, not at the cosmo, but at the mesoscopic level, to survive in this world governed by the laws of physics. So I think, and have argued, that it is really flowing, and our brain creates this conscious perception of the flow because it's a real part of what we experience, and of the universe.
Yeah, that's a cool new word for me, mesoscopic.
Mesoscopic.
Yeah.
Generally, we would say macroscopic. Microscope. You don't need a microscope to see it, but mesoscopic feels a little more authentic, like the meso being middle.
Right.
Yeah.
So, Dean, we've created memories, right? So that's us understanding some timing. And I can travel backwards in my mind and revisit memories. I am present in the now, but I can throw myself forward with an imagination of what might be in X time going forward. So as the physics of that, as opposed to the neuroscience of that, how do we interpret? And are we actually time traveling? Because we experience time dilation when we dream. I mean, your dream will last 30 seconds and it will feel like you've been in there for half an hour.
That's the whole plot line of the movie Inception.
Yeah.
Oh, I never saw that. Was it good?
Yeah. You go. I think that was the movie where you can go inside of someone else's dream, but the timing of it, the dream is way longer than the actual time frame. And if you do this a few times in, then it's a fraction of a second equals days or something, and so you have to budget for that as they go in and out of each other's dreams.
So what?
I only saw the spoof on Rick and Morty.
Oh, okay.
Fair enough. So are we now, if we're in the physics looking at this, is this a quantum state? And then how does the neuroscience figure this out from their angle of approach?
So I think it would be best to start that by looking at the neuroscience before we get to the physics.
Okay.
Because one of the unique things about human cognition, one thing that distinguishes us from most other animals, is our ability to do exactly what you're saying, Gary, which is engage in what we'll call mental time travel. Time travel, which is, you think of something as fundamental as the invention of agriculture, right?
Yeah. For
some, it's not that complicated, right? Plant a seed, reap the benefits later. But it evades most other animals, and it evades the ability of humans to figure that out for many years. And it involves mental time travel. It says, I have to do something now that will only give me benefits months or years into the future. And that was a very hard step for us to connect the temporal dots between things that are cause and effect over weeks, months, and years.
As an immediate cause and effect would be obvious.
Absolutely.
Right? You punch somebody in the face and they're hurt and they punch you back. That's an immediate response.
They know who to blame. They know who to
But
blame.
the seed in the ground, oh my gosh.
This ability to jump, make these cognitive leaps across time is an incredibly sophisticated thing we do, but we're still not very good at it. And that's a problem, right? Because, climate change,
Right.
we're not acting,
Right.
or saving for retirement. But I go back and I think about the first ancestors that had that ability to look into the future. And this goes back to what Neil said. Can you imagine what it was like for the first human to make this cognitive leap and say, oh shit, I'm going to die? Right? Because it's this ability to engage in mental time travel that we became aware of death. And many people have argued that there was a coevolution between our ability to engage in mental time travel and religion, because religion was the antidote to this vision that we saw, that we were going to die. So it said, well, don't worry, there's another life after this. And there's a great quote by Jorge Luis Borges that says, except for man, all animals are immortal, for they are ignorant of death. I don't know if that's true, but
What
it
a
captured
quote.
the point.
That's a great quote, even if it's not fully true.
Yeah. So with respect to looking into the future, though, I look in my backyard and I see squirrels going freaking nuts, no pun intended, in the fall, hiding food because they know that food won't be there. Is that not also a form of looking into the future?
Okay,
Or is it blind instinct?
yes. So that's probably the answer, Neil, is that they're programmed to do that. So a squirrel that never experienced a winter will still do the same thing. But not only that, Chuck.
Interesting.
Consider this, Chuck. Humans have been known to engage in future-oriented activities without necessarily thinking what will happen 9 months into the future.
Yeah, well, that's called screwing.
That's right.
Why do they do that?
You left that for our imagination, Chuck.
Oh, I'm sorry.
He was setting up so he didn't. So no one had to say that, Chuck.
Well, I mean, I said it for the kids.
Thank you, Chuck. But the point is that the squirrels are probably engaging in that activity because it brings them pleasure at that moment in time.
So we've been talking about memory like it's just a thing, like like memory on your computer. But our brains are, of course, organic tissue with chemicals and electrical synapses. And so, how is a memory actually stored? Can we just lay some foundation there?
Yeah. So one of the most fundamental tenets in neuroscience, and one that has been borrowed by artificial intelligence, by the way, is that information and memory is stored by changes in the coefficient or the weight or the strength of the connection between neurons or artificial units. So, we use these large language models, and how they store information is by just tuning billions and billions and billions of weights. And all those weights is how much each neuron influences the other. So if I'm one neuron and Chuck is another neuron, we can change the strength of the connection between those, and then it will behave differently and learn. And this is very fundamentally different from what Neil referred to in terms of a computer memory. So in a computer memory, there's a very clear dichotomy between the memory and the computations being performed. So there's the CPU and there's the RAM, and this is the standard von Neumann, so-called von Neumann architecture. In the brain, that distinction doesn't make as much sense because it's the activity flowing through these networks that is both the computation and the memory. So it's extraordinarily hard to separate those two things in the case of human memory.
Ooh, wow. That's really, that's very cool.
So I've read some connections between this discussion and Morse code. Like, how do they relate at all?
Well, so there's two aspects to Morse code, right? One is understanding code and one is the timing. So they're both valid questions, but the memory part is sort of not that different, whether you're doing Morse code or you're doing normal language or you're reading. You have to store information. But the timing is unique in Morse code, right? Because there in Morse code, everything's the duration of the dot or the dash and the interval between them. So how does the brain do that? So this gets to Gary's original question, is how the brain tells time on this scale. And that's been a mystery. It used to be thought it was due to oscillations, but our work and other people's work has shown that that's probably not the case. It has more to do with neural dynamics. So imagine, we're a bunch of neurons, and I'm neuron that activates Chuck, and Chuck activates Gary, and Gary activates Neil. So that forms a dynamical system. It forms a trajectory in neural space, and that you could use that to tell time. So depending on who's active, so Neil might be the last one to be active. So if we know if he's active, is he firing, that means that 1 second has passed. And if Chuck, maybe that's 500 milliseconds. So the brain is this dynamical system, and these patterns of activity can become a clock, if you will.
Holy moly.
Interesting.
That is fascinating. So these, now there's a saying, neurons that fire together, wire together.
That's a saying? Where'd you get the saying? In the hood? What?
This is not in the hood, man. This is not in the hood, man.
Where have you been hanging out, Chuck? That's a saying.
That's hilarious. So what I'm wondering is, when you think about this dynamic grouping, could you then change? Could your brain either falter and fail with these groupings because of misfiring, or could you change it in some way purposely because you get these neural pathways to kind of line up and fire together?
Yeah. So that's a really great question, Chuck. And it relates to what you just described. Neurons that fire to wire together is called a form of Hebbian plasticity. It's a course of associative plasticity named after a famous Canadian psychologist, Donald Hebb. And that was sort of the original algorithm that how do neurons figure out who to wire together? And it's a very powerful algorithm. And it says that if I see your face, my visual neurons are firing. At the same time, my auditory neurons might be hearing your name. So maybe it's a good idea that those auditory neurons and visual neurons hook up with each other, because then I can now see your face and then recall your name. So it's a very, very powerful, simple algorithm called associative synaptic plasticity. But back to the timing, you also have this ability to generate sequences. So if I say A, B, C, D, you predict what's going to happen. Or in music, if I go da, 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 you can also fill that in. So there, you need to not only just fill what's happening together, but what's about to happen. So that requires another rule on top of this idea that associative, that neurons that fire together. It might be that neurons that fire first wire to the neurons that fire second. So there's all these levels of different algorithms on top of each other. But you're exactly right.
So this brings a question of, because so much of when any of us learned about the brain, it was, well, this section of the brain is language and this is facial recognition. So this is very spatially mapped. And most of this conversation just now is a temporal mapping of the brain, which is a whole other dimension here. The space-time of the brain, this time thing all feels very fresh and new to me. Is it new in your field?
It absolutely is, Neil. And, I'll make the point that I think time is at the center of a perfect storm of scientific problems, from free will, consciousness, determinism, how the brain works, even AI, and the more fundamental question of the nature of time. So I think time is complicated, more complicated than space. What do I mean by that? That's a bit hand-wavy, right? But what was probably the first field of modern science? I would argue that the first field of modern science was probably geometry, right? There's not many things discovered 3,000 years ago that we still teach in school, like Pythagoras' theorem. So why was geometry the first field of modern science? It has no time. Geometry, as originally developed, was timeless. It's static. It's not changing. It really took 2,000 years and the likes of Galileo, Newton, and Leibniz to really bring in time and dynamics and add time to space. So, and I think neuroscience is in many ways at that same stage where we've ignored time and we're just maturing enough to start addressing these complex questions pertaining to time.
I can add to that the syllabus sequence in physics matches closely how this actually got discovered. So the simple, like you said, geometry, there's no time dimension in any geometric calculation at all, right? And so you move forward, there's none in trigonometry either, or in algebra, physics has to come in. And early physics, time was kind of simple. You move this this far for 3 seconds, and then you turn left and you go another 10 seconds. Later on, and this, I remember this like it's yesterday, when we finally had these functions that changed over time. So it wasn't just a force pushing, it was a force that changed over time. We had to track that. And this involved differential equations. A whole other layer of math had to go on top of the math we were previously using. And that's really what separated, that's what, if you were going to drop out of physics, that's when it was going to happen, typically.
And without calculus, we wouldn't really be able to deal with time to the degree that we need to. And that's the foundation of modern science, of the economy and technology and so forth.
And there you go with Leibniz and Newton, the two sort of, I was going to call them fathers of time, but they're parents of time.
So, Dean, we have something called a temporal window of integration. Now, correct me if I'm wrong here. So if I'm talking to you personally, face to face, I will see your lips move before I hear the sound that you make, right?
Yeah.
And the brain fixes it?
Yeah.
So is this now the illusion of time?
Wait, and is that because the light signals to your brain are processed faster than the auditory signals?
So there's two things there. So let me just, to make sure we don't confuse them. So obviously, because light travels faster, a lot faster than sound, I see your lips moving reach my retina more rapidly than the sound reaches my ear. But, and this is the tricky part, the sound processing is actually much quicker. So if you see me clap and I ask you to react to the sound or to the sight, your reaction time is actually quicker to the sound. So they say ping pong players, I'm not sure this is true, so they say ping pong players sometimes react to the sound of the ball before they see the ball, because the brain processes auditory information. And that's because the retina is incredibly slow. The retina relies on biochemical reactions. And so, but we do have a window of integration. So whether you're sitting in the cheap seats in a soccer stadium or the expensive seats, we can adjust this window of integration. So it's adaptive. We can tune it so that if you're watching a movie up close or far, it seems everything's integrated. As long as it's in a window of 2 or 3 or 400 milliseconds, your brain can fix it. So in that sense, it's just your brain being flexible and sort of trying to align time and space. And this is something, I don't know if you know what the McGurk illusion is. The McGurk illusion is if I say ba, 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 but you see a video of me saying ga, 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 your brain mixes those things and you might hear something like da, 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 because you're mixing audio and visual in your brain all the time, whether that's time or space. So yes, this window of integration is extremely important, but adaptive. The brain fixes it for you like magic. It's like the editing programs you guys will use for this podcast.
So actually, we're all in one big kung fu theater movie from old school Saturday afternoon, just like, so you kill my master.
So that's a great example, Chuck, because those are so bad it's unfixable. Right. The brain can't deal with that degree of messing up in the kung fu movies. That's exactly right. I like the imitation, though.
Neil, how about Einstein's general relativity, where time slows down depending on the proximity of objects?
Yeah, no, but in neuroscience, it never slows down for you. You just always have your time. And it's all happening to everybody else.
Yeah.
And you only know it's happening to everybody else because you're measuring it. So that's not a neuroscience. You guys might think about that, Dean, but I don't care. However slow you think I'm moving, my pulse is still doing 70 beats a second, and I'm listening to my music, and you're the one with the problem.
So the time is different for us, or different places, different.
Yeah, for gravity, for speed, all manner of things can famously shown in that scene in the movie Interstellar, where the astronauts go down to the gargantuan planet near a black hole, and the black hole slows down the time, but you're there with them and they're just living their 15 minutes of time. And they get back to the spaceship and the guy's got gray hair.
Yeah, of course, it's the black dude they left up there to get all old. They get back, he's just like, oh my God, where you been?
It was the black guy they left up on the
How do you sync that with the arrow of time if there's this distortion going on and it's a flow forward?
Well, both would be flowing forward, but as Neil said, you would never know that time is slow for you. You're incapable of knowing if it's fast or slow. Only when the problem is when you try to sync between two people are in these different frames of references, that becomes a problem and raises paradox. But this relativity brings this question that we started off to: is the past, present, and future equally real, eternalism or not? And this has extremely important consequences for Hollywood. Because, we, as I think Neil said, is that pure fiction that you could time travel in real physical space or not? And a presentist like myself would argue, no, it's absolutely impossible. And an eternalist would argue it's at least theoretically possible.
Well, okay, but then you have cause and effect issues with that. So Dean, famously in the film Total Recall, and Chuck, who was in Total Recall?
I
think he's a little more literate than that, a little more articulate.
I'm having trouble recalling.
In the film Total Recall, which is surely on every neuroscientist bucket list to watch, they just implant your vacation in your head. And it's a memory that you never experienced. And of course, this also hints at everything that happened in the Matrix, where everything's just implanted. And so many episodes of the brilliant hit series on Netflix called Black Mirror involve people uploading their memories, downloading them, replaying them. And so where do you think the future of this is? And how real are those portrayals of your field?
Yeah. I think that's a great question. And I think a lot of that relies on sort of a simplistic understanding of the brain as a computer, that you can somehow hook it up to an external device. And, this is a very topical issue, right? Because companies that use brain-machine interfaces, most famously Neuralinks, the Musk company, are attempting to do this. And I think some people have the idea that, yes, if we have all these wires into my brain and they're hooked up to a computer, that we will be able to, I'll all of a sudden be able to speak Mandarin, or I'll be able to fly a plane. I don't think I'm
or you'll know Kung Fu.
Or know Kung Fu. More importantly. And then I'm very skeptical of those notions, because I think they don't really capture how the brain actually works. Because as I was saying before, the brain is not like a von Neumann computer, which has a memory module and it has a CPU module and it has a bus module that you can upload things. There's no clear separation between the memory and the computation. So I think you'd have to really modify how our brains work to upload things. So somebody might say, well, all you're doing is just interfacing the brain directly with these external computers, so then I can fly the plane or do Kung Fu. But really, it's not me that's doing it. It's the computer that's doing it. So you're just changing the interface. And the brain already has some pretty nice interfaces, right? They're called eyes and ears and hands. And the brain is very slow bandwidth. So I don't think we can dramatically enhance the bandwidth by magically implanting 1 million electrodes in our brain. So I'm skeptical of this. And you're probably familiar with Ray Kurzweil's arguments too, that we'll achieve the singularity by melding with an AI. I think that really isn't consistent with our understanding of neuroscience at this point, in my opinion, Neil.
That's insightful for you to mention that if you're plugged into all these wires and then you know Kung Fu, it's really the wires that knew Kung Fu, not you. It's just feeding you that information. Mm. Is it really you at that point? It's the AI that's doing it.
Yeah. But can it sync your lips to your speech? That's what's really important.
You're still stuck on that.
So, Dean, before we wrap this up, and I think we will be shortly, is it actually possible that the brain is the only time machine that physics will allow?
So the answer to that question, in my mind, the answer to that question is yes. Because as a presentist, I don't think time travel in physics is a possibility. So when people look at things like wormholes and from general relativity, what general relativity says is that wormholes are a theoretical possibility. They're not really a prediction of general relativity. It says, well, it could happen depending on the assumptions that go into the equations, the initial conditions, and so forth. But I would argue that, yes, the closest we'll ever get to a time machine is our mental time travel. And that, in my opinion, actual time travel is a theoretical impossibility. I understand maybe Neil disagrees, maybe doesn't, I don't know. But
you're in good company with Stephen Hawking, who, as much as he would have welcomed time travel, in fact, he hosted a party for future time travelers where it was...
And nobody showed up.
He chose a time and a date, and said, anyone from the future who can time travel, show up now. And then nobody showed up. So he advanced something called the time travel prevention conjecture. It sounds like that if it's not exactly that sequence of words, where he's suggesting that one day we will discover a formal law of physics that prevents the time travel, which then prevents the paradoxes that have been such fertile content for time travel movies. And my last question to you, sir, professor, is, and I have my answer on this, but I want to hear it from like a real neuroscientist. Do you think the human brain is smart enough to figure out the universe? Or is the human brain smart enough to figure itself out?
Okay.
Ooh, bam.
That's so first place. Neuroscience is the most recursive field in science, right? Because it's the only field in which the thing being studied is doing the studying.
Mm-hmm.
So that's a problem. There's reasons to
think?
It gives me job security, put it but put it this way, there may be reasons to believe that no system is capable of understanding itself. So I happen to think that we might be able to pull it off, but maybe with AI, to answer Neil's question, we might be able to understand ourselves. But his first point was understand the universe. And I think this is a bit of a trick question, that what does it mean by understand? But the answer to your question very informally, I would probably say no in one way. And that, quantum mechanics is a good example. Do we understand quantum mechanics? I don't.
We just calculate with it.
That's exactly right. So
you shut up and calculate.
So the math the brain has serious constraints. It has serious bugs. It has cognitive limitations. The greatest debugging device we ever invented is called mathematics, because mathematics allows us to simulate, to model, to capture things we don't understand. So as Neil said,
don't understand intuitively, right?
Yes, exactly. Mm-hmm. So if you mean understanding intuitively, I don't think, most of the interpretations in quantum mechanics I do think are basically revolve around limitations of the human brain.
Yeah.
So
I'm with you on that. I was a little on the fence, but you pulled me back onto your side.
I was always on your side because I think we're stupid.
Yeah. So Chuck, to go along those lines, there's this debate in AI whether AI is as smart as human beings are, but human beings are pretty low bar.
Exactly. I'm with you 100%.
Yeah. I agree.
Listen, Professor, I've enjoyed this conversation. You sound like you're like totally in it, and we might want to reach back to you to see what your next scores are on the human brain and what we can accomplish with it. When did your book come out?
This has been out a while. This came out in 2017.
2017. Okay, give me the full title again.
Your Brain is a Time Machine, The Neuroscience and Physics of Time.
Love it. Love it.
It's been a great pleasure. So thank you, Neil, Chuck, and Gary.
You're welcome.
You've got it. Well, this has been yet another installment of StarTalk Special Edition. And we're loving these neuroscience interviews. Gary, Chuck, always good to have
you. Pleasure, my friend.
Always a pleasure.
Professor Buonomano, you're on our Rolodex now. So don't be surprised if we call on you again. Neil deGrasse Tyson, your personal astrophysicist. As always, keep looking up.